Removing a conformal coating is often the first task we're confronted with in the repair process. They're put on for a variety of reasons. For insulation, to protect from corrosion, sometimes to hide what's underneath. Our problem is to remove them as much as necessary to get to the circuitry or components underneath. And we need to do it in a way that won't damage the board or the component. There are several different methods that can be used.
Solvents to dissolve them. Abrasion techniques to wear them away, powered by miniature machining equipment. Sometimes a thermal parting tool with a heated tip to over-cure thick resins so you can dig most of the way down. And for some cases, a hot air jet that can soften them and break them down.
In general, you'll be dealing with several main types of coating. Some of the earliest coatings were the acrylics and varnishes.
Not used much anymore, but they'll probably never disappear altogether. This one is an epoxy resin, one of the most common of all, but it's now being replaced by polyurethane. The polyurethane coating can be either hard or soft, and like the epoxy, either thick or thin. Here's one of the RTV silicone ones, synthetic rubber. It's primarily used for potting submodules. This last one is one of the newest and was specifically developed for the electronics industry. It's trade-named Parylene.
It's always vacuum deposited on the board in a thin, hard coating, and it's very uniform and tough. They all have their individual characteristics, and some of them are easier to deal with than others. Let's take thickness first. We can abrade away a thin coating much more quickly and easily than a thick one. The epoxy resin on this one is 1/8 inch thick, so we'll need a two-step approach. We'll use one technique to rapidly thin it down to where we're close to the board surface, and then a second, more precisely controlled method to remove the remainder without damaging the board. After thickness, we determine how hard it is. We can take a pointed object and try pushing it into the coated surface. Is it hard, soft, in between? This tells us what type of abrasive to select. Next, we consider the transparency of the coating. If we can't see through it at all, it may be a silica-filled coating, and there's no telling what's underneath. So we'll have to go through it very slowly to avoid damage. And finally, we determine whether or not it's soluble in a mild solvent, one that won't, by itself, do damage to the components or the board. Thickness, hardness, transparency, and solubility. When you pick up a board with an unknown coating, these are the important characteristics that you need to know before you can select the proper method for removal.
Let's take this board to begin with. The coating's thin and transparent, so acrylic lacquer is a good possibility. Using xylene or another similar mild solvent, a test is made first, brushing a small amount on a non-critical area. It dissolves. So now solvent is applied to each of the solder joints at the repair site. Several applications may be necessary to completely remove the coating and prepare the area for solder removal.
In most cases, we need remove only enough coating to get to the area being repaired. Sometimes, though, removing all of it from the board may be required. This is usually done either with a continuous flow of fresh solvent or by soaking the board in a series of solvent baths. The primary caution with solvents is to be sure that the work isn't damaged by them. Harsh solvents, like the chlorinated-based ones, need to be used very carefully.
Pre-soaking in a bath of Freon TF can sometimes be used for removing an RTV silicone. The Freon will soften and expand the rubber and loosen its bond to this connector. Then it can be easily slit, peeled, and chipped off.
The use of controlled low-temperature heat is the basis for the thermal parting method. It's the best way to handle the problem of thick coatings. A special tool called a thermal parting tool has been designed for the job. It's temperature controlled and comes with tips of various shapes. They have no sharp edges. The low temperature used allows you to over-cure the coating and break it down without burning or charring it or producing toxic fumes.
In use, the appropriate tip is selected and inserted, and the temperature set just high enough to break down the coating, but not so high as to burn it. The thickness of the coating around the component body is gradually reduced, taking care not to contact the surface of the board. As much coating as possible is removed from around each of the leads and the body of the component. In this case, the leads are going to be clipped so that the body of the component can be pulled free after most of the coating has been removed. Heat is now applied to the component itself in order to break the small bond that still holds it in. It may take a moment or two of heating before the coating is soft enough. Then it comes out easily. After the component body is out, the remaining coating material is removed. Then the leads and solder joints will be removed by solder extraction. A hot air jet can also be used to weaken the final bond. An alternate method for attacking hard, thick coatings is miniature machining using ball mills. This system provides a low RPM at high torque, and you can manipulate it quite easily. Notice how the side of the ball mill is used. That's the most efficient cutting area, not the end of it. Here again, the object is not to remove all of the coating. You could easily damage the board or circuitry that way. You want to just thin it down.
Remember, the strategy is always to go first from thick to thin, using thermal parting or machining to get most of the coating off. Never attempt to actually reach the surface this way. There are other methods for that step. And another caution, don't use soldering irons for this work, even ones with modified tips. High temperatures and sharp edges can damage the board. Once we're down to a thin coating, we switch to abrasion techniques. And again, we'll use the powered miniature machining system.
Because of its high torque and constant low RPM, you can get controlled and precise removal of coatings without any mechanical damage or overheating. Our workpiece indicator in abrasion is a visual one. By watching the changing color on the surface of the work and the brightness of the circuitry, we can remove thin layers of coating with great sensitivity.
High RPM systems, those running at 5,000 RPM or over, are not recommended. They can cause dangerous frictional heating and usually don't have sufficient torque to remove the softer, gummier coatings. Let's watch the abrasion method on a board with a thin, tough coating of polyurethane.
The work begins with a fine, rubberized abrasive. These are ideal for hard coatings on flat surfaces. The tool is moved in a circular motion to minimize heat buildup and lower the risk of abrading through the circuitry. A bristle brush is then used to complete the removal, since it will conform more closely to the contoured surfaces. The brush is also the best choice for soft, thin coatings. At low speed, it doesn't clog up like an abrasive wheel does. The final step is always a thorough solvent cleaning prior to desoldering. And then, around each of the leads on the component side, the seal needs to be broken to provide an air passage for vacuum desoldering. Here it's being done with a thermal parting tip. You could also use a bristle brush to do it.
Abrasion is the primary method for removing thin coatings. A second one is a hot air jet.
You can control the air temperature and the airflow rate and apply the jet to almost any circuit board on either side without causing damage. The temperature setting depends upon the particular coating, and a good test is to direct the jet onto a cleaning tissue from about 1/4 of an inch away. At the correct temperature, only a slight scorching will occur. The jet can handle extremely delicate work since the tip never touches the board itself. Here it's being used to soften a thin polyurethane coating. Light pressure from a wooden tool helps to remove the softened or over-cured coating.
We have then a number of effective methods for coating removal. The choice depends on which of these types of coatings are involved and what their characteristics are. You've seen the acrylics and varnishes handled by solvent, RTV stripped and peeled, epoxies and polyurethane handled by thermal parting, abrasion, and hot air jet. This last one, though, we haven't singled out yet. Parylene. It's tough and can be uniformly deposited very thin. Sometimes it's no more than 0.02 of an inch thick. Parylene's fairly new and therefore often may present a special problem. The fact is, the removal method is similar to that of other thin, tough coatings using abrasion techniques to wear it away. Here we see the procedure.
After a thorough cleaning with solvent, the air seal is broken around each of the leads. On the circuit side, the coating is abraded through using a tapered, rubberized abrasive wheel. Enough is removed to permit full access to the joint by a solder extraction tip, and then the solder joints are removed. The work area then gets a very careful inspection under a 5 to 10 power microscope to assure that all traces of parylene have been removed from the pads on both sides of the board. If any does remain, it is removed with a rubberized bullet-type abrasive, which also serves to roughen the surface for replacement of the new component. You have to be sure to get every bit of it off any joints that are to be resoldered, and on both sides of the board, particularly if the area is to be recoated after repair.
Recoating a board requires knowing the specifications of the original material and having some of it or its equivalent on hand. The methods used depend on the type of coating. Most can be applied by either dipping, brushing, or spraying.
The dipping method is one that gives good coverage, but it's difficult to mask off any area of the board or to get very thin films. Some blobs and runs are almost inevitable. Brushing is probably the simplest way, but here again, it's hard to obtain a thin coating, and you have to be careful not to leave bare spots. Spraying or vacuum deposition are the preferred methods if you have the process equipment available, and masking can be used to protect what you don't want to cover.
In the field, however, where you may not be able to dip or spray, the rule of thumb is to spot remove the coating and recoat with a brush, covering the spots and adjacent area with a thin generic coat. In all cases, you need to meticulously clean the surface first and pre-tin them to prove they're not contaminated. And in some cases, you may have to bake them afterwards to remove all traces of the solvents and moisture. Before attempting any recoating, make sure that the coating material and the cleaning system you're using are compatible with the board and components. If you're planning to recoat a parylene-coated board, the task of preparing the area for the new coat is a bit more involved. You'll need to be meticulous in removing all traces of the original coating and then pre-tin the circuitry to make sure it's parylene-free. Here we see the steps in the process.
First, the existing coating is completely removed. Next comes pre-tinning each of the holes, which is then followed by extraction to remove all the excess solder. The area gets a good cleaning with solvent. The new component is soldered in, and the area gets cleaned again with solvent. You'll find a full presentation of what we've covered in your handbook, so we'll stop now. Your instructor will want to review the material with you, and in the notes section of the handbook, have you write in the particular specifications, standards, and practices of your organization. Then we'll move to our next lesson, damage repair.